preparation. Hope you enjoyed this morning's general sessions. Today's breakout tracks address specified related issues that affect our industry, with this one focusing on connectivity and technology. You should note that the sessions will be recorded and posted to the members only section of the website, so don't see anything that you don't want everybody to hear. If you're asking questions at the end of the session, we'd ask you just to wait for the staff to hand you a microphone so we can record your comments and also hear the response from the panelists. So I'd like to go ahead and introduce our speakers. We have Jim Costello, Chief Technology Officer of Telefonix, Inc. Jim has more than 25 years experience in the wireless communications industry, including over 20 years developing solutions for aircraft connectivity. Jim's most recent position was with Road 44 as Vice President of Engineering. Prior to Road 44, Jim was with Motorola as Director of Advanced Technology and with Verizon's Airphone Business Unit as Vice President of Product and Service Development. Mark Schwartz, President, Design Consultancy Practice at Telefonix PDT. Mark founded Product Development Technologies, or PDT, 20 years ago. During that time, Mark grew the business into a full-service product development firm with over 120 employees and more than 80 awards for its work. In 2013, after years of successfully working together on aerospace product solutions, Telefonix and PDT's competencies were joined into one integrated team to drive innovation in the IFEC and aerospace industry. So over to Jim and Mark.
Thanks.
So when I was a young engineer, I was always taught if you were going to be doing technical training after lunch, tell everybody that there's going to be a quiz at the end, just to keep everybody on their toes. But this time around, we're going to actually do the quiz at the beginning of the presentation. So I just wanted to ask the audience, who might actually remember what these products are that are up on the screen? Okay, there's a
new model in the front, not the new logo.
So if you go to the next slide. So basically, though, if you had guessed that that was an actual Verizon phone, you would be right, along with the cabin telecommunications unit. What's interesting about this, though, is that the cabin telecommunications unit that was shown on the last slide was actually designed in 1991, and that phone was actually designed in 1995. If some of you are old enough to remember the 777, when one of the IFE vendors was going to be late, we were asked to go and design a phone that could go on the bulkheads for Inmarsat satellite. Well, what was really remarkable, though, is if you look, the CTU was manufactured between 1993 and 1998. A colleague and I were just flying recently to China, and lo and behold, taking a walk around the airplane, what did we see? But that phone was still mounted on a wall. And basically, we're talking about products that were still on an airplane 22 years after they were first developed. Now, never in my wildest dreams would I have ever imagined seeing that on an airplane in 2015. But it just goes to show you that when you take a look at products, and we talk about obsolescence, sometimes the product's out there in the field much, much longer than you ever would imagine.
So if we drew a parallel to what we're all used to in cell phones, could you imagine if you had to try to source parts for that bad boy? So I started my career at Motorola, and this was one of the first cell phones that I got to work on. And you know, most of us haven't even seen one of these in 20 years, let alone think about the airline industry and the longevity of those products. So one of the things we're going to do today is, as mentioned, I run a design firm, and we're majority owned by Telefonix. And we combined our resources 6 years ago to start to move into more electronic boxes and stuff. But the cool thing about it is, as a design firm, we work in multiple industries, so we're able to learn a lot from the other industries that apply into the aerospace industry. And so the beginning part of this talk is going to be me dwelling on some experiences we've had on the non-aero side, and then Jim's going to tie those in on how we can learn from those in the aerospace.
So if you take a look at the airline world, it's really not that much different from the commercial electronic side. When you look at airline requirements and internet service providers, in-flight entertainment providers, really the focus really comes back around when it comes time to actually define the contract as end-of-life management. How are you going to actually support the product going forward? Basically, when you look at requirements that might say you have to support a product for anywhere from 10 to 15 years. In addition, there's obviously product performance. Everyone wants to know exactly what it is that your product does and how well is it going to perform against customer expectation. There's the recurring cost, product support, and just upgradeability. Upgradeability means designing in a modular format such that when it comes time to actually improve the product, you have the capability of going into the unit and making that upgrade without it being a large capital expenditure. But basically, you can't do B through E. It can't be accomplished unless you look at end-of-life management or obsolescence management from day one.
You know, in the parallel universe, in consumer electronics and medical devices, things move much faster. I mean, all of us keep our phone for like a year, and then we get a new one, and it has all kinds of new bells and whistles every year. So it becomes quite challenging for the airline industry to keep up with that pace because people expect things to work like their iPhone. So what we're going to touch on today is probably not the most exciting topic, but it is necessary. It's all about the life of the product and being able to source the parts throughout the life of the product. And in this case, aerospace, as we know, is long, so it's more challenging. So we're going to touch on a few things. First product draws a parallel to the medical device world. This device is a life-changing device. It's for diabetics. It happens to be very iPhone-like, but it happens to take care of your diet, exercise, and accounts for everything and measures your glucose real time so that you get glucose injections through an insulin pump automatically throughout the day, which means you never crash and you never go too high or too low. So it's really life-changing. Here's the challenge, though. Just like the aerospace industry, it's a relatively low quantity product with a long lead. So I think the takeaway from this particular product and the learning point is that when you're developing the architecture for a product like this, it's important to pick your vendors at the very earliest stages so that you know you have a partner going forward. Don't get tied to a 5-inch resistive touch display. Go out and find what's available and be able to adapt early on, because if you just lock down your product description early and battle through at the end, you'll find out that you don't have vendors available. So the key takeaway for this product in parallel to the aerospace industry would be flexible at that early architecture age. Here's another, this one has all airline products beat. This was a device we worked on. So in 1941, an engineer at the Perkins School for the Blind, which is where Helen Keller trained, he embarked on designing this brailler, first of its kind for blind people. And you can see the 1950s design influence there. That product is still sold today, amazingly. The guy did such an amazing job designing it, and we were tasked with designing the next generation one. So obviously, not that this ever kind of still holds and people still use it, but the problem is it's heavy and expensive. So we really did not redesign it because you couldn't get the parts anymore. We redesigned it because it was time. It was over 50 years. So the cool takeaway on this one, I think, is the fact that this particular product can be supported around the world by any number of people. So when designing products like this, which you could find on an airplane also, it's important to make the parts incredibly easy to source. So in this case, there's 500 unique mechanical parts in here. Most of them are off the shelf, but a lot of them are just simply machined. So it is practical for someone on the other side of the world, even without drawings, to fix their own devices and not have to have the actual drawings and everything. So it keeps it completely sustainable. Here's another example of a technology challenge. We'll start to see this in aerospace now for sure. This is a device we designed for Dell. It's the thinnest laptop in the world. It's only 10 millimeters thick. But the challenge with when you're pushing technology to the limit is finding vendors at all. So I have a 10 millimeter thick laptop and I have to figure out how to open it. Ended up having to invent electronic latches to do that. Single source vendor. Another one was it needed a fan. Now, the CPU portion of this is like 6 millimeters thick. So you have to find a fan that's basically 3 millimeters thick if you think about that. So when you have those technology challenges, you're going to be probably tied into one vendor that has that on the roadmap. So when you get into those situations, it's encouraged to get into a contractual agreement with that supplier. All these slides have addressed hardware. This next slide kind of talks about software and software upgradability. You know, there's been a revolution out there, Android giving you license-free software with all the plugins that it comes with. I don't know if any of you ever knew that the software upgrades in Android are done alphabetically. So when you hear the crazy terms, ice cream sandwich, jelly bean, Kit Kat, and you're like, what? Now you'll be able to know which one's the latest because all you gotta do is your alphabet in your head real quick. So that's actually how that works. Jim's gonna talk about one of the aerospace products we did a little bit further down the line, which was designed around the Android architecture, which is really nice because even though the hardware has a long sustaining life, if you leave yourself the ability to upgrade to the latest level of Android, for example, your customer is going to get that latest and greatest experience for a long sustaining time, even though the hardware may be fixed.
So designing for upgradability, what does it really mean? I mean, what we're really talking about here is, to some extent, obsolescence management. When you go and you actually design a product, we try to break it down into what are the 3 major steps that we want to view when looking at doing an initial design, what's important. So obviously requirements, everyone really understands what that is in terms of collecting information from the customers as to what it is that they're seeking. Ongoing technology review, looking really and making an assessment of where the technology is today. And then customer commitment and product roadmap. And I'm gonna walk through each one of these and try to take the analogies that Mark had talked about when it came to consumer products and talk about how it relates to the aviation space. So first, if you take a look at requirements, this just happens to be a server that we had designed a couple of years ago. But if you take a look at where the customers are coming from, what is it that they all want? Well, they want the product to be as low cost as possible. But at the same point, then they also want at least a 10-year product life with technical support. So that really kind of puts you into a spot right away where you're immediately starting to look and say, okay, I'm going to have to do part of this design off of custom off-the-shelf equipment. I can't necessarily go and design all of this in order to support, number one, with the lower cost. But number two, if I'm going to be buying COTS components, then I have to really be able to assess where it is in its product life. Obviously, from an airline perspective and also from an airline OEM perspective, once you release the product and once you've actually qualified it, no one ever wants it to change. You know, and that's kind of a nice starting point, but I think we all recognize the fact that that's never going to occur. There's always going to have to be changes, either along the lines of manufacturing changes because capacitors aren't available, all the way through performance improvements where a product might be available for 5 years and people say, well, couldn't it operate faster? Where you're actually looking at making processor improvements. But everybody always comes in with that same going requirement of you can't make any changes, you can't roll the part number, you can't do anything once you've actually qualified the product. And then the other thing with the airline industry, and I'm sure you're all aware of this too, is there's not very large volumes. You know, if you produce 500 to 2,000 pieces of any given component, at least when it comes to electronics going into an aircraft, that can be quite a lot. That can be quite a large volume. And it might be that a customer wants product, say 100 pieces in year 1, and year 2 he wants 200, but by year 7 he only wants 50. You have to be able to at least plan out and look forward as to what might be the potential requirements from a production standpoint. So that's just really from a commercial life cycle cost management. On the other side, there's the technical side. And when it comes to any type of active electronics that we're working on today in the aviation industry, one of the biggest challenges we have is how to handle power dissipation. More and more of the electronics are higher powered, the processors and the like. But what you see is we're given less and less space to actually package that equipment. So from that perspective, heat is never your friend. You want to be able to cool things in order to increase the reliability, but at the same point, there's certain bounds put around you if you follow some of the ARINC requirements as to how large is the box and how much heat can you dissipate. Obviously, from a thermal condition standpoint, no one ever wants fans on board. They never want to. They may allow you to do air cooling via plenums, but they don't want fans to be installed. And the challenge with a lot of avionics today is the E&E bay is more and more filled to capacity with active electronics, and you have to find other locations where you can put boxes on an airplane. So you often are put into a point where you have to either do conductive cooled or you have to have some type of integrated fan to dissipate the heat. And then the last item I just have up here is from an MTBF standpoint, mean time between failure. Basically, the customers out there today are looking for MTBFs anywhere from 35,000 to 70,000 hours plus. That, again, is just a theoretical calculation when you're doing the design, but it's becoming more and more important that we're able to choose components early on that can actually be able to support that high level of mean time between failure, which in most customers' minds relates back to reliability. And from the commercial side, customers are always looking for extended warranty. It used to be that 2 years was a lot. Now most customers come in with 5 as a minimum, and they're not accepting anything less. So again, reliability and warranty come into effect quite a bit when it comes to upgradability. If we take it to the next level, and then we actually try to break down and demarcate where the functions of hardware, software actually happen within an LRU, you know, basically most in-flight entertainment connectivity equipment really centers around a handful of critical components. Whenever we do a design, we always look at what are the top 10 critical components that are going into the box, how are we sourcing it, and what's the availability for upgrades or options for us to be able to provide alternative vendors. Obviously, one of the first items is computer processors, and in most cases with the in-flight entertainment equipment, it also includes Ethernet switch capability. Mass memory drives, gosh, they keep getting bigger and bigger. You know, we're putting in boxes today 800 gigabyte size drives. They're now just going to 1.6 terabyte drives. So the drives are always increasing because the IFE vendors want to put more and more of their content locally stored on a box. So from that aspect, we have to continuously look at where is that equipment going. We have the aircraft 429 in most cases in discrete interfaces. Most of the in-flight entertainment equipment too does have integrated into wireless radio modules. And you might say, well, what does that really mean? Well, when you're on the ground, oftentimes people don't want to use the satellite systems or the air-to-ground systems for taking data on and off of the airplane. It could be billing records, it could be diagnostic statistics. So oftentimes we're putting wireless radios integrated within the box. And then obviously the other component, and this is the one that usually has the most effect on mean time between failure, is power supplies. Power supplies, you know, are usually, the problem with power supplies is they're usually the product that gives off the most amount of heat, and they usually have the lowest reliability. So from a design standpoint, it's always critical to look at the power supply design. So we talk a lot about hardware, but as we talk about software, and Mark talked about the Android example earlier, some of the basic questions that we always ask ourselves is, are we going to be responsible as the equipment manufacturer for providing the applications that go on the equipment? Most times in the case of in-flight entertainment and connectivity, that's not the case. We may only provide the lower level software, but the actual applications are being provided by the service providers, because that's really their niche of how they're presenting content to the users. So, you know, another item that's really critical too is looking at the software itself for the operating system. Are we going to go with open source, or are we going to be using something that's more proprietary where there's license fees involved? Those are questions too that we have to draw out of the customer as to which way they want to go. And then, you know, one major fundamental question that we always have to ask ourselves is, who's going to maintain the box after it's released? You know, from a manufacturing standpoint, you know that you're going to have to maintain it for bug fixes and for upgradability. But from a software standpoint, you always have to ask the question, who's really going to own that responsibility? Is it going to be the service provider, or is it going to come back to the manufacturer? So, you know, if we've gone from technical requirements of asking the questions out there as to what it is that customers are seeking from us, then we have to look at it back on the other side, and this is where the trade-off against requirements actually comes in hand. So, you know, I know this is easy to say, but hardware and software designs always have trade-offs. We might think that it's very easy to pick and choose which path that we go, but it's not the case. You know, in most cases, in-flight entertainment connectivity systems are not considered, or considered non-flight critical. So we have some flexibility there. But also too, from that standpoint, we also have to look at cost again, back to reliability, back to support. And from a design standpoint, we often have to look for industrial grade hardened components that go into the box. And when I say industrial temperatures, I'm talking about wide temperature swings, minus 15 to plus 70 degrees, if not greater. And here's where the trade-offs come in. Oftentimes IFE vendors have to provide displays. You're not going to find LCD displays that are going to have that wide of a frequency range, temperature range. So in those type of instances, we're kind of put into a spot where we have to look and see, well, how are we environmentally going to control it such that those components aren't going to fail and they're going to still operate within the parameters of the original manufacturer. So as we start to look at the requirements and the trade-offs, we also have to start looking at how are we going to procure the individual components. Now, a good example is when it comes to processors. Oftentimes, if you're buying COTS equipment, the processors are supported anywhere from 5 to 7 years. Well, if you're starting to design tomorrow that you know is not going to be in production for another 18 or 24 months, you don't want to find yourself falling into year 4 or year 5 of that product life of that processor. You want to get moved much earlier in the product phase of release, which often means that we're taking on more of the challenges and the risks that we could have problems early on. But again, we're looking at long-term life as to where we're going to take the product and how we're going to support it. And then finally, if we develop an overall roadmap, we want to be able to make sure that any of the components that we're choosing, or as many as possible, have an upgrade path, meaning that we have alternatives in place that we can use different components from the same component from different manufacturers, say it has the same bus architecture, that allow us to be able to pick and choose the vendor's componentry that's actually going into the box. It's highly critical at this point, given the fact that we know obsolescence is eventually going to happen. And from a standpoint of identifying the product roadmap and the management, we have to make sure that we actually have people that are going to be following and tracking the technology. Because if you don't do that, you take your eyes off the ball. You might be happy today, but find out tomorrow a part is no longer available. So I'll give you an example. Mark gave a number of case studies relative to consumer products. We've recently been working on a satellite modem manager. It's a unit that provides the modems for operating over a KU or KA satellite system. Well, one of the things that we ran into right away was the customer in this case wanted to have a long product life, and he wanted to make sure that we were going to be doing some optimal trade-offs in terms of processing power versus availability on a product roadmap. Well, one of the first things that we had to do was we had to look and say, okay, we know we have to support this product for 10 years. We have to choose a processor that's within year 1 of its life from Intel. We couldn't pick something that was even a 3rd or 4th generation. We had to go much later along the lines of the development cycle in order to be able to support a product that we knew that we were going to have to be able to stand behind for the next 7 to 10 years. And then once we chose a family of processors, then we had to take a look at power dissipation. If you recollect what I mentioned earlier, power and heat, usually go against each other, and when it comes to your friend, heat is never your friend. So we had to look at ways that we could come up with ways of providing proper cooling for these advanced processors, and or at the meantime reducing the power capacity, the performance capacity of the processor, and distributing the intelligence to other components within the box. So one of the things that we chose going along this was to follow a modular processor engine. So we chose a path of ComExpress, which allowed us to have at least 2 or 3 different vendors that provided the same processor capability on the same bus architecture, that we could know that we could drop in a different processor if one of the other vendors decided to get out of the business. Another case that comes along the lines too is when it comes to mass memory storage. I mentioned earlier about Intel makes drives now that are 1.6 terabytes that are 2.5-inch SATA drives. Well, in this product that we were designing, we didn't have enough room to put the 2.5-inch SATA drives in. So we actually had to start looking at different technologies relative to memory. And we had started going down one path of following an mSATA product line, and as we started to look more and more at vendors supporting mSATA format, which is a specific or physical format, and bus architecture, we started to find that there's less and less people supporting MSATA. And as we looked at the technology roadmap of the memory vendors, like Micron and the like, we started to see more and more of them going into this format called M.2, which kind of looks more like a pack of bubblegum when you were a kid, type of a size drive. And it fit very well within the physical architecture that we had in the physical space that we had to work with. So one of the things that we really started to identify is every couple of years the memory technology is evolving. It really follows the NAND flash technology. As that advances, more and more memory start to increase. So just in this example, we thought we had a path that we were going to go down, that PER, with an MSATA packaging, and then we quickly decided, you know what, we're not sure that if in 3 years or 4 years those same parts are going to be provided anymore, and subsequently we made some changes. The other is firmware. Mark had talked about software earlier, and software is one of those trickier products in terms of support and how you're going to do it. We tend not to change operating systems in aircraft equipment. That really starts to induce a lot of regression testing, a lot of changes relative to changing part numbers, which is never a good thing. But when it comes to firmware, we're always looking at doing updates to firmware where we can see some improvement in performance. But what that means is that when we start any type of program, we have to have some form of a design verification matrix that says, here is everything that we're going to test against this piece of hardware and its software functionality. And anytime we're going to go and make a considerable change, we're going to have to pick what tests we're going to have to perform regression testing on. And what we've always found is we've always gone to the customer first and say, do you want this firmware change? Here's the enhancements it gives. It's your choice. And if so, here's what we're going to go back to and we're going to run regression testing on to ensure that the changes that we've actually introduced cause no harm to the system. This just happens to be a device that was actually designed by PDT. It's actually a wireless telephone that goes in Bombardier aircraft.
Yeah, so this particular device is designed to give you the experience of a full smartphone on your private aircraft. I'm sure you all have one of those. But anyway, yeah, we decided to go with Android in this device because we knew that in this demographic that the expectation would be every time you came onto the airplane, you wanted the latest and greatest. So this device, actually, you can push down the software. Once you do testing on the side, you can upgrade the software. But the one thing you have to be careful of is that each software upgrade does generally require more power and more memory. So it goes back to the road map selection when you're picking the processor and the memory, that you're looking ahead for what's coming down the road.
And I think in this situation, the two of the biggest, I'll call it risk items or product obsolescence issues that had to be addressed was in the battery and the display.
Yeah. Obviously, it's this ties together a bunch of things that we've talked about: technology, interest of a vendor. It's really hard to get a vendor to put a battery on an airplane when the quantities are so low. What vendor wants all that hassle for such a low quantity of units? So one advantage of working in neighboring industries is, in one respect, we're working for Dell and they're making tens of thousands a week. And then we're able to pull in those favors with those battery suppliers and say, come on, help us out. We realize this isn't the most attractive amount of quantity, but typically we can leverage that as an advantage.
So just in summary, if we look at upgradability, and as Mark kind of started off with, this isn't the most interesting topic of the world, but I don't know anybody who doesn't build equipment that every day you're getting some type of end-of-life message from some component vendor, and it's causing you grief. If we can do anything going forward, what we really have to do is anticipate that day one. Taking the requirements, breaking them down, and understanding that the implementation is going to have hard trade-offs. You're always going to have gives and takes with the customer as to, I can do this, I can't do this, especially when I'm looking at something long-term to be able to provide support. Temperature is always the one that comes of interest. Can you control the temperature within a box such that we can take a part that's maybe doesn't have as wide of a temperature range and have it work. You know, there's trade-offs of what we can and can't do in any type of design. And then designing with the components at the beginning of their life cycle. I gave you the example of Intel. We know that if we're going to pick an Intel platform, we know how many years we're going to get support. It's very critical at the beginning of a program that we design to the earliest stages. Even if we're taking some risk of taking processors early, it's better to do that than taking them too late in its product life cycle. When the maturity level is there, and it limits the risk on the design, but it also means that the part's not going to be available. Same thing with memory. I gave that example earlier. Memory is a great one. Technology is changing so quickly, you have to keep your eye on and keep talking to all the different memory manufacturers to understand where is the products going in the future. And then lastly, customer commitment in a product roadmap. I can't say enough that, you know, it's very important to engage the customer along with making these decisions. It can't be in a vacuum, because there is the give and take. But if you can accept that any type of long life product that you're going to have in the field is going to have some changes as you go along, because you're going to look for product improvement. As long as you can communicate those changes to the customer, and even day one be able to predict, hey, I know this product is going to go obsolete in 2019, but we believe this technology is going to evolve to go into this other path, but we know that we're going to be able to get a part that integrates with the board. That's really important to be able to convey that confidence to a customer that you're not going to be left out on the side of the road and not be able to get support for the product. And then the other is just to continuously monitor what's available in the marketplace. Because again, we could find ourselves in a position where you just don't want to come in that morning and find out a product's been end of life when you thought you had 18 or 24 months still left of it. You always have to be looking for alternatives to replace that part.